then the input match between the two terminals of the antenna is going to change. I have a chip here with fixed input impedance. If I change the input impedance of the tag relative to the input impedance of the chip, then the optimal operating frequency is going to shift. This shift is going to relate it to how much change in the permittivity in the substrate material. And I can relate this change in the permittivity of the substrate material to either temperature or humidity. For example, here I have a Kapton material that's in brown reddish color, and these are silver ink or strips of silver ink. On the back of it, this one front, one back, you can see that these are creating capacitance. And we know that the capacitance is depending on the area and the thickness and the permittivity of the material between those two areas. So if the medium is changing humidity, this Kapton material is going to sense the humidity and change the permittivity of it. Then the capacitance is going to change, the equivalent capacitance is going to change, the input impedance of the tag is going to change relative to the input impedance of the chip. And the change of the optimal operating frequency is going to be indicative to the change of input impedance that reflects in terms of permittivity that's also related to the humidity. The same thing we say it here. If we have a bucket filled out of water behind this area, and if I can heat this water, I'm going to change the permittivity of the water. And the same concept. The temperature change in the water environment is going to be related to permittivity and related to optimal operating frequency and so on. So when we do this, for example, in this humidity sensor, this is basically the construction of it, and these are the silver inks. And this slide here shows you also how the capacitance is being configured for a total capacitance of the system, and this is how the operation would work. Two different frequencies correspond to two different humidity of the medium itself. The difference in frequency is going to be indicative of the humidity itself. Now, the optimal operating frequency is the minimum of all these curves. And these are done for different kind of permittivities that you should have a lookup table between the permittivity of the material and the humidity of the medium itself. In water temperature sensors, you can see the sensor here, water bucket behind it, and another reference sensor that doesn't have water bucket. So the operation of this sensor in the same environment here, this is going to operate at specific frequency. This is going to operate at different frequencies because we have a heater behind it, and we keep heating. There is a heater and thermostat behind it. So we heat the water, and we measure the temperature, and we measure the optimal performance using the tag formers device. And you can see that the minimum of these curves give you the optimal operating frequency, and they are at three different temperatures that are being set for the bucket of water. This is another device that's been constructed and built and assembled, and the software, hardware, by one undergraduate student who took about a semester and a half. He basically built an inventory system, handheld inventory system, and these are the components of it. RFID development kit that has a communication board, Raspberry Pi, a battery, and on one side we have a connector here for the antenna to be connected. The outside is basically LCD screen and keyboard. So you can carry this system and walk into any warehouse and collect all the information about the tagged item, store it in an SD card, or communicate with the communication board to the host media, and basically transfer the information. So this he started to learn about RFID, got into the development system, and this entire frame also he printed it using 3D printer and put everything together. Another application is a robot here. Again, has Raspberry Pi development kit and Arduino to control the motors that control the wheels. We use large antenna because this entire robot was supposed to work inside a mine. A close-up picture for it here. And this is the tag that was in the mine, and this is the antenna. So this work was the initial work. The follow-up work is what you see it here. I have Robert students who finished his master degree on this system. You can see a helmet here, 2 circularly polarized antenna connected to the helmet. The antennas are being designed with the same students who designed the antennas that I showed it to you before. Robert put the system together in terms of development kit, inertia moving system, and put the software, the handheld device, and the antenna. And inside the mine, we placed tags along the walls with specific coordinates, and he can wear this jacket and walk into the mine and figure out where he is in the mine. So basically, it's an inverse localization system. We have multiple tags located at specific coordinates, and we would like to know a miner walking into the mine, where is he exactly? And the reason for this, because he is going to carry another dust monitoring system, and he is going to measure the dust density at that position. So we need to know the map of the dust inside the mine with location as well, to be able to determine is it safe for someone to walk there or not. So this student got his master's degree based on this system. We tested this system outside the mine and inside the mine, and these are the system component. You can see an image of the tag of the antenna that's been designed. The tag is placed on a wooden holder here and hang it on the mine at specific positions. This is the inertia measurement unit and RFID development kit. So the localization system does not depend only on RFID system, but also depend on the inertia IMU unit, and depend on another technique called map matching. In this system, you can see 2 antennas and 2 readers, because it was easy to put tags on each side of the mine and get the antenna to basically radiate on both sides and read the tags that they can read inside the mine. This is an illustration for the mine, and basically students started to walk here, coming here, going through this way, going up, going this way, coming back, and going back to the same position. When he used the IMU and RFID system, all these dots or these traces are basically the positions that are predicted by the system. Knowing that we are in a mine, and on this trace, if we do map matching, then basically the system is going to give you these positions. And you can see a perfect match on the mine trace as well. So that's basically how it was done at this time. You can see that this system is very bulky, and right now we are working with 2 students to convert this entire system into a handheld system. So it would be no helmet, no big antennas, and so on. So those are 2 of the applications that we have done recently. Do we have many? Okay, I'm going to go quickly on military applications, and you can see where tags can be placed. Specifically, most of the time they are active tags, except maybe here is passive tag. Why do we use them there, or what are they being used? In management of equipment, inventory, personnel as well. We need to know where they are all the time, and controlling access to sensitive area. The benefit to the Army is that it improves the inventory management, replacement of manual procedure, improving labor and productivity, elimination of duplicate orders, and increased visibility and accountability, and fuel and temperature monitoring via sensor tag as well can be done. Containers and their contents, we can track them, monitor their movement, and so on, and then track any item, equipment, tool, documents, people, armory or ammunition, and all these things. This is the benefit to the Army itself. the people who are supplying supplies to the army, there are lots of benefit for them as well. I'm going to skip on this because of time. So basically, you can do automatic recognition of items, automatic tracking, automatic alarming system, and history of traces or things are moving from one place to the other. In medical application, you can see more or less the same thing. Patient tracking or history of records of patient, we can track this, equipment tracking, and medicine and pharmaceutical tracking as well. So basically it's the same concept, except in medical environment, sometimes you need real-time traceability, for example, for blood samples or certain kind of medicine. If you really have a need real-time traceability, then you need to have active tags working all the time. Active tags use RF signal. Medical equipment, there are so many other medical equipment use RF signal, so there might be some interference there. And that's something that is a little bit of difficult. It has to be managed accurately, where to put active tags, where to put passive tags in the medical environment. Again, you can manage equipment, inventory, personnel, and control access as well. And applications is basically what I mentioned. And I would like to thank all those people that we worked with me on all these topics. Two professors from Tampere University of Technology, University of Mississippi. Fan Yang was with me at University of Mississippi, now at Tsinghua University. Dr. Georgian right now in Colorado School of Mine. He and I was working on the robots and handheld units for the miner. And then many former students that are doctors right now in different places. I have undergraduate students also participated in these projects, and current students working on some of these applications. So the rest is basically some of the publication with links, and I'll be glad to give you this presentation if you would like to go to some of these links and download those papers that are only related to RFID area. So I think I'm going to stop here. I took too much time, more than what's allocated time. I welcome any question here or comment. Yes?
I have one question regarding the antenna that you mentioned about the negative gain. It was a circular antenna with some rectangular patches. You mentioned that the gain was around 5 dB, and this antenna, I think, was painted on FR4. What's the reason of this high gain?
The separation between the antenna and ground plane. Yeah.
It was a filter.
Yeah. Yeah.
Actually, thank you very much for this very interesting lecture.
Thank you.
I have two questions regarding to the sensors. You are talking about mainly two types of sensors, one related to the humidity and the other is related to temperature. When we are talking about humidity, you claim that the substrate is absorbing the humidity from the atmosphere. When the substrate absorbs the humidity, I think it is not a reversible operation. You know, I can use the sensor for just one time accurately, but after that, does the humidity will release out of the substrate and return back to?
It depends on the material that you are using.
Yeah, I'm talking about the Kapton material.
Yes. We managed to be able to measure it at different humidity environment and get the figures that I have with different minimum value is at different humidity level.
Could it be used multiple times?
Yeah, I don't see any reason for not.
I'm talking about the change in the material construction itself.
What you are, I think your question is that if I increase the humidity from this point to this point to this point,
exactly,
can I take the
release
humidity out? Can it come
yeah,
back?
Yeah.
And
we use heating to return back to the original situation of the substrate?
that's his question, yeah. And my guess, yes, but I can't say 100% it does go back. It doesn't make sense if it doesn't go back. If we are using a material that's not going to go back to its original states, if I change the humidity, then the sensor is not going to be very good
I'm
sensor.
asking this question because some of the compounds, especially in substrates, when it takes humidity from the atmosphere, it makes some kind of combination. It's
Yeah,
combined with internal structure
Yeah, I understand.
on the atom, on the
I understand.
particle level. Yeah.
I hope we have a chemical engineering
Yeah.
one here who can answer this question. I'm
My-
not expert in
my
this.
second question: how do you measure the S parameter?
How do I measure the S parameter?
Yes, S11 here.
The curves that I showed it to you are not S parameter.
Okay.
The curve I showed it to you is the optimal power to communicate with the sensor. And those curves are not measured with a traditional
So
device.
you bought a chip.
No. The tag formants
Mm-hmm.
equipment that I showed it to
And
you.
it has some kind of differential port.
No, the tag formants emits through the antenna different level of power.
How do you
And-
connect the antenna? The antenna has 2 ports.
Oh, the antenna is a tag
Yeah, the differential
connected
port.
to a chip. Yeah,
You bought a chip.
of course, these are chipped antenna.
Okay. And this wideband chip, it covers whole band, and you monitor the
No,
chip.
those two sensors were done in Finland and were done for the European band only.
Thank
But-
you very much.
But
Thank you, sir.
it doesn't mean that you can do it for other bands.
For sure, but I'm talking about the shift. To
The sh-
cover this kind of shift happening, you need the chip to have a wider bandwidth compared with not just a single bandwidth at 915, for example, that is the standard in the United States.
Most of these sensors are very limited in frequency change. So
Yes,
I don't think you
agree.
are going to have one sensor that covers the 3 Europe, United States, and Japan. It's going to be focused on the center frequency of each one of those regions.
Okay, thank you, Doctor.
You're
Thank you very
welcome.
much.
Okay.
Same for the temperature.
Yeah.
Temperature sensors. Now I am measuring the temperature in certain region. That how much. Then if I go to another region, it will be storing the previous reading. So it needs cooling before reading another position or in sensing the temperature. Is
You
there a cooling system?
mentioned it needs cooling. So
Yeah.
if the temperature is not going to change, then the operating frequency is not going to change. So if you take the sensor in one medium and temperature is 20 centigrade, and then you put it in an environment where the temperature is basically 18 or 15 centigrade,
Yeah.
directly, whatever sensing material here needs to be adjusted to this temperature before it gives the indication of this media here.
Yes, yeah, it means again it needs cooling. Some sort of cooling or a fan to cool.
You can't
or
read
something.
it. You can't read it immediately. You can't change the location of the sensor from 2 different temperature
Needs a time.
regions
Ah.
immediately and expect the temperature to be immediately recorded accurately. Yeah.
Thank you, Doctor.
Yeah.
Thank you.
Thank you for your presentation. I have 2 questions.
Can you raise the microphone?
Okay,
Yeah.
I have 2 questions. The first question about fabric material. I see in one slide you have studies changed with WISH. How can I represent the change in permittivity of the material with WISH?
With what?
Washing.
I don't think the permittivity of the material change. The conductivity of the thread is basically changing with washing. And if the thread, which makes the antenna, if the conductivity of it changing, then the read range is going to change. If you remember in the tags that we design using silver ink, and we put 1 layer, 2 layers, 3 layers, 4 layers, look at it this way. You have a conducting thread, very good conductive. You wash it, conductivity goes down, and the read range goes down. So it's not the fabric itself that changes.
Okay, how can I represent it in my simulation? How can I represent these properties in my simulation?
Oh, in the simulation
Yeah.
itself?
How can I measure it?
No, measuring it is easy. That's what we
Okay,
measure. We wash the things and then we
yes,
measure
I
again.
wash the
Yeah,
fabric or the antenna using fabric.
Yeah.
How can I put it in my simulation? This is change.
The simulation can be done if you are representing the trace in a specific, the conductivity of the trace. For example, if we are using finite difference time domain,
Yeah.
these traces or the thread is going to have a specific conductivity. For a perfect conducting, we put, for example, 10 to the power 7.
Yeah.
Less conductive, 10 to the power 2, 10 to the power 3, things like
Okay,
this. So this changes the conductivity and changes the performance using simulation.
You say that I try and error, not exact.
No, what I showed you here is experimental results,
Yeah.
not simulation results.
Another question?
Yeah. Yeah.
You can push every time, and then by using the DAC unit to measure the relative permittivity. And then you put it in the simulator and to get the simulated results. And then measure the performance of the antenna to get the experimental measurement of the antenna. What is the problem?
Another question. Thank you, Dr. Another question. Silver ink, not perfect conductor, yeah?
No.
The same question. How can I represent it?
How can?
How can I represent it in my simulation? It's not perfect conductor.
The silver traces, you can put it on a.
I have a problem in that.
For the silver ink, you can deposit it on a wider strip, and you can use conductivity meter to see the conductivity of it before you continue with it. You're welcome.
We'd like to express our deep thanks to Dr. Sherbeni for this interesting lecture. We will have a break just for 20 minutes. يعني 20 minutes, and we will start inshallah as the next lecture after 20 minutes. Many thanks, Dr. Sherbeni. By the way, we can get a group picture together with Dr. Sherbeni in this location now.